I am going back to my lecture again. We have covered the digital filters. I'll come back to analog filters after spending few more minutes on the previous topic, that if you have observations R of n, which is S of n plus R of n of n, and the observations are available to you, L number of observations, for n is equal to n to n minus 1 to so on and so forth. And then the best estimate for S was given by the set of equations which are the Euler-Walker equations, and then we came up to the following, that the solution to this comes out to be, assuming this to be white noise, that's what he tells me is the last. Right? Because signal and noise are uncorrelated. So RSR will become equal to this, and the rest of them, since there is no correlation, it becomes equal to this. This was where we ended up in the last class, right? So the H can be obtained by inverting this matrix. So you get H0, H1, HCl minus 1, so on and so forth. And that will be the discrete filter, which will give you the best estimate of the R of S of n. So the solution of this will give you in S of n with minimum mean square error. If you just spend a second and recollect, the reason for this is that there is some amount of correlation between the signal samples from point to point, and we are extracting all that information by putting them in terms of the cross correlation of the signal 1, 2, 3, so on and so forth. And we also came up with a very important result called the orthogonality principle, where the error is orthogonal to the observations for all values of observations, and that is a very basic principle, the orthogonality principle. Philosophically, what it means is you have extracted everything possible from this set of R's that you have obtained or measured. There is nothing more that you can do. That's what the orthogonality really means. If something more you would have done, there would have been still some amount of correlation which you could have utilized to improve the estimate. And the best estimator pulled out every possible information that is available with respect to signal as well as noise. As a result, the error that you will get is orthogonal to any of the observations. That is basically philosophy behind the orthogonality principle, and which turns out to be the optimum principle when we went to the analysis. If we take up a situation where R of n is equal to some signal plus noise, where S is a deterministic signal number, a signal sample, some value, That means now you have observations, not just one observation on the signal embedded in noise. You have L number of observations for the same signal corrupted by different samples of the noise. And the noise samples are uncorrelated. Are you with me or not? Because if I make in this expression S(1) is some constant signal sample, which is same signal sample, but you made empty number of observations on the signal sample embedded in different independent noise samples. And then what is the best estimate for the S? Because what is available to you is this, not this. Given this, how do you get the best estimate of the S here? When you have L number of observations. That is the problem here, where the observations, all of them will contain the same deterministic value S, but embedded in noise samples. These noise samples are uncorrelated noise samples. So this is available to you, and from this you must get the best estimate of the S. So if you translate that problem to this equation, RSS 0, because a deterministic number, it will be all the same, isn't it? It becomes S square. So all these values will be S square, right? Because there is no question of samples of different times is the same value for all samples. So it is all, in every case it is S only. So this RSS component will become equal to S square. So this matrix move into S square plus sigma square, S square, S square, like this, the diagonal values being equal to are you with me? This multiplied by H0 to HL minus 1 is equal to, again here S square, all these are same. If you now observe here, this into H0 plus this into H1 plus this into so on and so forth. Similarly, second equation is S square plus S square into H0 plus this into H2, so on and so forth. So you can immediately see here, one answer is all H0s, HIs must be same. Because all HIs will have same equation. So all HIs must be same. That means the weightage you give to each observation, when you add them up, should be the same value. And what is the value of the weightage? Any equation you take, first equation for example is S square plus sigma n square plus S square plus so on and so forth into H sum is equal to S square. Any first equation. So from here you can find out what is H. H is equal to any HI. There is L number of them here, S squares, and only one sigma n square, and here S square. So the coefficients with which you weight the observations is all same value, but the value is given by S square by L S square plus sigma n square. So finally what you will get here will be summation of all this. So you will get a final A, final S is equal to L times S square by into R, any R. Is it okay?